Bonjour. So welcome back to QX01, Introduction to Quantum Information and its Associated Technologies. So let's have a look at the program that has been modified slightly. So today we're going to look into Quantum Algorithm 1, so introduce the first quantum algorithm. We're going to see the Deutsches Algorithm. Next week, there is a UTT event, so there'll be no lecture. The week after that, there will be Quantum Algorithm 2. The time might change, though, might be at 2 p.m. We'll see. And then afterwards, we will have someone from the company Ketz, that's now confirmed, talking about quantum cryptography. That will be by Zoom. And then there will be, the week after, there will be someone from the French company Thales to talk about quantum sensors. That's also confirmed. And this most likely will also be by Zoom. Then there will be a lecture, probably given by myself, on Introduction to Quantum Error Correction. Most likely, we'll see how it goes, but most likely that's what I'm going to talk about. Then it's also confirmed that there will be someone from the French company Atos to talk about the quantum learning machine that they have, that they built and they work on, the Atos quantum learning machine. And then the last lecture will be given by a colleague from the University of Cartagena in Spain, and he'll actually be here, so he's going to because he's going to visit us during that week. So he's going to talk about different quantum technologies that we haven't talked about, so more about physics and technologies such as superconducting qubits in particular and trapped ions as enabling technologies. Right. So last time we didn't quite finish. So we went through quantum gates, and I believe we were at the last point, which was not really related directly to quantum gates, actually, but is how to create entanglement with photons. So I'll come back to that briefly, and then move on to quantum algorithm. So just a quick reminder. So the idea was in 2 slides to show you how in the lab we can create entangled qubits made of photons. And for that, the starting point, as a quick reminder, we went through that, so I'm not going to go through that again. But the idea is to see matter as being a series of atoms and electrons together in a piece of material, in a piece of crystal, and then see that the electron is linked to the atom by a harmonic oscillator. And if you do this, you can show that the equation, the Newton's equation, will look like this. If you drive it with an electric field, so you send an electric field to your crystal, and this is going to interact with the electron, and the electron is going to move, and his motion is going to follow that equation, where we have the acceleration part, you have the dumping part where the electron eventually will stop. You have the harmonic oscillator part, the driving part, what I call the driving part, so it's the incoming light that move the electrons. And then the point what I want to make is that, so this is in linear regime, but you can be in such a way that you are in a nonlinear regime, so any harmonic oscillator have a linear regime, but can also have a nonlinear regime. It's also known in mechanics, in sound waves, in all sorts of various systems where you have oscillations. And so what it means is that on top of the linear dependence with the distance x between the electron and the atom, then you need to add a term that is also called an harmonic potential, where you have an x squared. And that is at the heart of nonlinear optics, or in fact nonlinear mechanics here, or even any nonlinear processes. Because if if you have a squared here, that means that if you look for a general solution that's going to look like this, where the incoming electric field is a plane wave with a certain frequency, omega. So again, what it means in the lab, you just take your laser with a certain color and you shine it onto the crystal. You will make the electron vibrates and follow this equation. And what you can look for is that, so this is what I call the driving electromagnetic field. And you can show that this type of solution actually most likely fits this differential equation. So in fact, it is the solution for x of t would look like that. But then if you insert the x of t being cosine of omega t, what you end up with, because of that squared here, is you will have cos omega t squared. And if you have cos omega t squared, trigonometry, simple trigonometry tells you that you can write this as 1/2 plus 1/2 cos 2 omega t. So what it means is that now, thanks to that anharmonic potential, and in order to follow this equation, now that means that the x component will have a nonlinear response and will have a higher harmonics. So we started with oscillation at omega, and now we have an oscillation at 2 omega for the response of the electron. So that means that we have nonlinear process. So what does it mean in practice? That means basically that we send a given frequency, a given color of a laser onto our crystal. The crystal will let this laser go through, like any light through glass, but also will generate through this nonlinear term, if the electric field is strong enough, will generate now a different color or a different frequency at 2 omega. Okay, and that's what we call a second harmonic generation, because you started with a given harmonic omega and you end up with an harmonic of 2 omega. And again, so what it means is that you basically now created a different color going through your crystal. So what you have is, thanks to nonlinearity, you end up now with 2 different frequencies, omega and 2 omega. And you can actually have higher orders. So here you can go further. This is a Taylor expansion, so you could have an x cube, and you could have a 3 omega term and 4 omega, and so on and so forth. And people actually do that in the lab, where they try to create as many harmonics as possible. Of course, these processes, the further you go down the line, the less likely they are, and the more powerful electromagnetic field you need to add. But if you stick to second order terms, so the squared here, with the laser, you can generate this frequency at 2 omega. So, okay, so how do we do this in the lab? Well, this is basically the experimental setup. So what it means is that you have a crystal. So in this case is a BBO crystal. BBO stands for beta barium borate, whatever. It's a non-linear crystal. So you have a crystal like this, and you take your laser, and you send the laser through your crystal. And what I showed you before, this process here is going from omega to 2 omega. So in terms of light, that means what? That means you come up with a red photon, less energy, to higher energy at 2 omega, which can be a UV photon. But in physics, there is the reverse process where you take a UV laser, so ultraviolet laser, and you have typically a wavelength of 400 nanometers. So with this, it's pretty much in the ultraviolet color. And you send that to your crystal. And if you call this, so this is the equivalent now of the 2 omega that we saw, then you can have, again, through this nonlinearity, you can have the reverse process where now a high energy photon at 2 omega will give rise to a pair of lower energy photons at omega. So you start with a 2 omega photon, and you have two UV photons, and you have 2 red or infrared, near red photons at half the energy that you started with, so at omega. And and this is called spontaneous parametric down conversion, or SPDC. So spontaneous parametric down conversion, or SPDC, and it's the reverse process of the other process where you end up with the red laser with frequency omega, and you generate higher energy, higher harmonics of 2 omega of UV photons. I mean, the other process can be explained by classical physics, classical optics, no problem. This process, on the other hand, cannot be understood through nonlinear classical optics. This is a purely quantum mechanical behavior. But intrinsically, we can see it just as, as I said, the reverse process as the other one, where you come up with low energy photons and end up with the high energy photons. So again, this is not a course on optics or quantum optics, but just to be aware of this. Of course, in any processes of that type, we have to have conservation of energy and momentum. So energy is okay because we had two h bar omega gives us 1 h bar omega and 1 h bar omega. So energy is conserved. One high energy photons gives 2 low energy photons. And then the second is momentum, and that's why I drew the direction like this, because if what we call the momentum, so the wave vector Kp, P stands for pump, because usually we talk about the laser as a pump. For historical reason, you pump the system. But whatever, so K pump, and then what you end up with is 2. So if this is photon 1 and photon 2, then you have K1 and K2, so 2 different directions for the outcoming photons. And there's a general law in physics on top of the energy conservation, which is that the momentum, not the moment, the momentum have to be conserved. So what it means is that basically the Kp, the K1, and the K2 has to be to add to each other. Okay, so Kp equals K1 plus K2. So if Kp is straight, then you can see that you can make the parallelograms between the vector conservation. Again, whatever, let's just assume that this is how it goes, that you come that way and you end up with 2 spatially separated photons coming out of your crystal. Okay, so this would be your nonlinear crystal. And you can see on this, so this is what we have here, and you can see that actually the 2 photons, so the top one and the bottom one, so photon 1 and photon 2, they actually come out through cones of light, okay? And this is precisely because of this relation and this relation. But whatever, without going into details, so what you need to remember is that they actually come out as cones of light, okay? And so if then you take your crystal and you tilt it slightly, you can actually bring the 2 cones together so that, like it is on this picture, you have 2 cones now that can intersect into 2 points. And so if I take a cut along this plane here, this is what I get. I get 2 circles, and I get 2 intersection points. And these are the intersection points are the important points. Because one thing I haven't talked about so far is that for momentum conservation and energy conservation, there's also something that has to be conserved, is the polarization of light. And in this particular case, we use what's called a type 2 crystal, whatever the name. But what it means, though, is that when you create the 2 photons, these 2 photons, 1 and 2, have orthogonal polarization. Okay, so remember, we said you can see you can see polarization of light as being vertical polarization, horizontal polarization, also diagonal and circular. But if you look into the horizontal vertical polarization state, then that means that this one is, say, horizontal polarization, and this one is, say, vertical polarization. Okay, And so if the two cones are not overlapping, there's no points in between, then if you measure your photons here and your photon there, you're going to find that all these photons are H polarized and all these photons are V polarized. Okay. In fact, I'm going to use, like in the drawing, so V and H doesn't matter. But now the idea is that you bring, as I said, these two cones together by tilting, say, and you end up with two circles. If I take a cut like this, and I have here two intersection points, right? And what I know is that the top circle are photons with V polarizations, and this is the photons 1, okay? And the bottom circle is photons with polarization H, and that's the twos photons. Let's put it here. So here is the case for any of those on this circle, and here's the case for any of these on the circle. Okay. But now, what happens if I take the intersection here only? And what happens is actually a combination of the two cases. Because here, so if I again, so the photons are coming out like this, so you measure this one and you measure this one. And the thing is, when you measure this one, because you are at the intersection, you can find H or V, right? Any of the two possibilities is possible. And in fact, if you take 100 photons, if you make 100 measurements on this photon, you will find that on average, indeed, 50 of them are H and 50 of them are V. Same for the other side. The other side, because you are in an intersection, it could be V polarization or H polarization. You cannot tell. And you cannot differentiate because the energy is the same, so the colors are the same. So again, if you take 100 of them, 50 would be H, 50 would be V. But there is a correlation from the start, is the fact that when we created them, if one is V, the other one has to be H. This is by energy and momentum conservation. It's given by nature. So it means that for each occurrence, you don't know what you're going to find. So say you could find H for this one, but what you do know is that if you found H for this one, then this one has to be V. And vice versa. If you find V here, then this one has to be H, because they have been created like so. One is H and one is V. Okay? But because on each point, any of these two possibilities is possible, so once is V, then is H. Once is H, then is V, and so on and so forth. But at a given point, the two possibilities are equiprobable. There is no reason why I could differentiate between one or the other. So that means that the state, the wave vector, the wave function of the state, so in ket notation, is actually one of the Bell states that we talked about, psi minus. Actually, it could be psi or plus or minus. It depends on various factors, but whatever, which is going to be 1 square root of 2. That's just normalization factor. But it's going to be that state, and I'll explain what I mean. Which is what? Which is a superposition of both of two possibilities. Either the first one, which tells you that photon 1, so if now I call this 1 and this 2, is H, then 2 has to be V. But as the other possibility is equiprobable, then that means that if I find V here, I've got H for the other one. Okay, so I've got H1 V2 plus V1 H2, because the two possibilities of the two photons are equiprobable. And as I cannot tell, in general, in quantum mechanics, I cannot tell which one is which. Then I put a superposition. Then it's a superposition, so I put a plus or minus. Question.
What will happen if we only have one intersection point between the two cones of light?
Well, first of all, you cannot have only one. So the question is, what happens if you only have one intersection point? Well, what you would have is a mixture. So if you mix everything in one point, you have a mixture of the two. But the problem is that you need, in order to have entanglement, you need two physical systems. What I'm talking about here is that this one goes this way and this one goes this way. So I physically separated them so that one can go in an optical fiber somewhere and the other one can go somewhere else. What you're saying is that, so you would have that state, yes, but you cannot differentiate spatially which one's which. So you would lose some information. You wouldn't have this perfect state that you have here. Okay. Well, so basically, using that technique, which is still used in the lab for people who work on photons as qubits, it's still used quite a lot, or various ways of doing it, and maybe integrated into optical chips and so on. But the fact is that is still a good way of having entangled one of the Bell states, so two of them actually, plus or minus, directly out of this experimental setup. Okay, this is the first generation of entanglement with photons was using this, and it's still used in the labs quite heavily. So here you have a famous picture where you have, so you see three rings, so you see blue, green, and red. And what you can see, so those are the three different angles, two different tilt. And you can see, for instance, that for the green curve, you are approximately in this position where the two circles are about the same size, and you have the two intersection points here, 1 and 2. Okay, so what you do then optically then is you pick up these points. So you can use, we do that in the lab all the time. We use irises and we just select spatially that part and that part, and that directly gives us an entangled state for the two photons at once. Okay, right. Okay, so enough physics for now. So let's go back to the following. So now let's talk about quantum algorithm. So in this part, there will be 6 subparts. So first of all, before starting quantum algorithm, I want to talk about some famous criteria called the Divincenzo Criteria. So David Divincenzo, I'll talk about this, gave some criteria in order to build a quantum computer, and I just want to state that. I think it's the right time in order to see what is required to build a quantum computer. Then, to talk about algorithm, I'll say a quick word, extremely quick word on classical algorithm. And I'll mention different families of quantum algorithms. So of course we will not be able to see all of them, but we will see some examples. One of them, one example of a mix of the two is so hybrid classical quantum algorithm. So I'll show you just in a couple of slides some practical implementation of that, where you could probably use the best of both worlds. And then we'll go to actual quantum algorithm that have been designed in the years. And I will start with the first example, perhaps the easiest example, and perhaps the least useful example, but just to give you an idea of how a quantum algorithm can gain over a classical algorithm through what's called the Deutsches problem or Deutsches Algorithm. And then, not today, then there will be a lecture on more practical algorithms. So one of them is called the Simon algorithm, and perhaps one of the most important algorithms so far in quantum technologies is the so-called Grover search algorithm that will be done at a later stage, and most likely not by me. So, I just want to talk about the so-called Divincenzo criteria. So this man, so David Divincenzo, published an article in 2000 called the physical implementation of quantum computation. And in this original article, Divincenzo provided a list of five criteria in order for one to build a quantum computer. And you will see after that since then, two others have been added. So two other criteria have been added, more related to quantum communications. So what are these five criteria? The first criteria is that you need a scalable physical system with well-defined qubit. Okay, I mean, it makes sense, seems to make sense, but actually this is by far not trivial at all. So what you need is, so I put here the equivalent of these electron spins we talked about. So, okay, cool. You can have, as long as you can have as many electron spins as you want, then it's okay to tick the first criteria where you have a scalable physical system in the sense that you can reproduce as many qubits as you'd like, equivalent qubits for your system. That already is something extremely difficult to do at present day. Okay, we cannot have as many qubits as we would like, and in particular, not as many qubits that look alike as we would like. Okay, and the problem of scalability is not trivial at all, and this was not addressed 10 or 15 years ago. People were more interested in implementing qubits on the system, and some of these systems actually died off because there was no way we could actually build more than 2 or 3 qubits, which was basically a useless system. So you need a physical system that is scalable so that you can add as many qubits as you'd like. This is already, as I said, not a trivial problem at all. Second criteria is you need to be able to initialize the state of your qubits. Okay, so you need to say, well, I want to initialize all my qubits to the 0 state. Okay, or everyone is at the 0 state. Or I want to have a particular superposition state of everyone is 0 plus, or everyone is 0 plus everyone is 0 except the first one, plus everyone is 0 except the second one, and so on and so forth. So, and this is more complicated than this, but again, it depends on the system. For some system, to actually initialize all the qubits to a given 0 state is not trivial at all. Okay? So again, it seems like an easy task to do, where you say, yeah, well, it's like you start calculation with your computer. You want to set all your bits of information to a given state, so 0, 0, 0, 0, 0, and then you start your calculation. So in a quantum computer, you want to do the same, but again, this is not that easy. The third criteria, which is a purely physical system, is you need what's called long decoherence time. So we kind of touched upon that, is the fact that we're talking about qubits. So qubit means that we are in a superposition state or entangled state like this. And this, as I said before, so it means what, for instance? It means that your electron spin is in a superposition of being up or down. But in quantum mechanics, as I said before, we mentioned it for operators and measurements, anything that could potentially measure your system or have a peek, have a look at your system, will change the state of it and will break the superposition state. So, and that's what's called decoherence. Okay, so you lose the coherence of your qubit. It's no more a qubit, it's just a bit of information because it went from 0 plus 1 to 1 or 0. It's what we talk about, the collapse of the wave function. So when you make a measurement, this is what you do, but that's because you control it. You want to control your qubit, you want to measure your qubit, you want to have the result. The problem is that when you have in certain systems, for instance, in superconducting qubits, we're talking about superconducting materials with superconducting circuits. And there are many reasons why in this material you can have decoherence, so you can have, say, charges moving around that can actually kill the superposition of a given qubit. So that means that you have a decoherence of your qubit, and basically you lose the superposition. So what that means is that you always have decoherence, you will always have decoherence, because you will always have something that at the end will kill your superposition. But what you want is to have long decoherence time, so that you have time to manipulate your qubits, to make your gates, your algorithm, your whatever, before something broke the superposition of your qubits. So you need long decoherence time, and that, yet again, is by far not trivial at all in actual physical implementations. You need, we talked about it, you need a universal set of quantum gates, of course, so that we said. So there could be the Pauli matrices, for instance, X, Y, and Z, and the C0 gate. This is one example of a universal set. But as I said before, you have many other type of gates, of single qubit gates and 2 qubit gates, depending on your system, because some of them is quite hard to have a C0 gate, for instance, so you want to have another 2 qubit gate. Whatever the gates your system gives you, as long as you have a universal set of single qubit and 2 qubit gates, then you're okay. And that, yet again, is not something that can be easily implemented in a lot of physical systems. And finally, the last criteria is that, well, you have a series of qubits, so you have to think of physical systems. So I talked about spins, so electron spins. So what you have here is, for instance, a piece of silicon, and you have a particular atom here where you can manipulate it, that it looks like an electron spin you can manipulate. So you have one here, one there, one there, one there, and so on. You can have, so I talked about trapped ions. So you trap atoms in an optical trap. So physically, you have a chain of atoms. So there's atom 1, atom 2, atom 3, atom 4, and so on. You can have superconducting qubits, which are made of several circuits, superconducting electric circuits. So you have one here, one there, one there, one there. So you have physical spacing, of course, like transistors, into your system. And the fifth criteria is that you should be able to make a cubic-specific measurement capability. So what it means is that if you have a series of qubits, so 1, 2, 3, 4, 5, and so on, you should be able to manipulate and measure this one, or this one, or this one. Okay. So you should be able to say, I want to address qubit number 1, or qubit number 5, or qubit number 126. Okay. And only this one, not the 5 others around it, or not all of them, or all the entire family. Whatever. So you want to be able to address a particular qubit. And that, yet again, is not easy to do in some physical implementations where you have, for instance, for trapped ions, if you don't do anything special, the entanglement is given by a collective motion of the atoms. And if you have collective motion, that means you cannot address easily single qubits, single atoms. So those are the 5 criteria. And if you look into a typical talk given by someone who works on building a quantum computer, somehow at the beginning or at the end, most likely he or she is going to give you this table with the 5 criteria, and you will see whether there is a check or a cross, or yes, we did it, or no, we haven't done that yet, or this is to be done. Okay. But so far, of course, no system has managed to do all of these perfectly. Because if it were to be the case, then we would already have a quantum computer, a universal quantum computer. Afterwards, there were 2 other criteria that have been added that are more linked to quantum communications, which is a strong part of quantum technologies. The 2 others are the ability to interconvert stationary and flying qubits. So what does this mean is that, so this is actually, so what I put up here is, so these pictures are from an article from 2008 that was published by Jeff Kimball called The Quantum Internet. And in this article, so Jeff Kimball, so that gentleman, thought of, what the quantum internet would look like if you go beyond quantum computers. What is a quantum internet, what it would look like? Well, what he says is that if you want to make a quantum internet, then you wouldn't have to have quantum nodes. So this could be, say, quantum processes. And then you would have to link them with quantum channels, like we do right now. So when you have a network of computers, you have optical fibers linking them, for instance. Except that now, of course, to link two quantum processors or two quantum nodes, you also need a quantum channel. Okay, so you can't just use a classical channel, just an optical fiber. You can use an optical fiber, but the information inside has to be quantum. And then in each of these nodes, this is where you can have this interconnection between what he called the flying qubits, which are relating one node to another, and the stationary qubits, which is physically at a given space. So for instance, if we talked about, so in his case, what he had in mind was a series of optical cavities with a single atom trap in each cavity. So this system here, so cavity plus atom, is basically a quantum node. And you could link these two cavities through optical fibers and through the so-called flying qubit, which in this case would be photons. Okay, so photons are good. Well, it's the best carrier of quantum information, quantum of qubits that you can think of. So this would be two nodes and the quantum channel in between. And of course, if you want a quantum internet, then you need to do this and to build with many, many stations and many, many channels in between. So you need, at this stage here, and this one, at each node, so that's criteria number 6, to be able to convert the quantum information that is present, so say the electron spin, for instance, that you manipulate, to map it to optical photons so that the photons, or these flying qubits, can then take the information away, the quantum information away, to the next node, and to the next one, and to the next one. And that's the second criteria within these two added, is that you have to have the ability to faithfully transmit flying qubits between specified locations. So that means also that once you convert your information to photons, then the photons is going to go to the next node, but in between this quantum channel here, that means that the information has to be safe and secure and remain quantum. Okay, so in order to faithfully transmit the quantum information from one node to the other. Okay. So there are people working onto that. So right now there's a big push into converting locally a processor, a small quantum processor made of, say, electron spins, for instance, which cannot be moved. So they are spatially on a piece of silicon, and usually they are in a cryostat at extremely low temperature, and there is no access to it. So the idea is, how can I now convert the quantum information from this stationary location to a flying qubit, so photons, and then extract it from it more easily to go to perhaps another node, another simulator somewhere else. Okay. So you need what are called quantum transducers in order to collect the quantum information from one system to another. So, and most likely through photons. Right. So I just wanted to have a quick word on these Divincenzo Criteria 5+2, because, as I said, they're very important. And if you were to watch a seminar or a talk on how to build a quantum computer, then most likely the people would show you where they are or what their system can do in connection, in particular, with these 5 Divincenzo criteria. Right. So now let's see what we can do with this in terms of algorithm. So I just want to when we talk about quantum algorithm, it's the same as before. If we talk about quantum bits, then before you talk about quantum bits, you have to talk about classical bits. So before I talk about quantum algorithm, I have to talk about classical algorithm. So if I take a possible definition of an algorithm, it's a process or a set of rules to be followed in calculations or other problem-solving operations. Right? So example, the easiest example, one of the easiest example is a search database where I give you a database and I ask you to find the number 33. So this is a search algorithm. It's usually what you would do is a sequential search where, like here, you would go through each of the possible data. So first one, 10, 14, 19, 16, 10, and then eventually get to 33, which is what you want, and you stop the algorithm. Okay, so this is a classical, and what it would look like. This would be an example of a linear search where you have an array A, and you want to look for the value X. So in this case, the array is about 10 numbers, and then the actual number you want to look for is 33. So if you were to write this in some form of computing languages, then it would look like this. With step 1, set I to 1, so you start the first one. Then if I is bigger than 1, then you stop, because that means you actually went through all of them. So you go to step 7, print element not found, because you've been through all of them and you didn't find it. It's possible. Then otherwise, if AI equals X, that means you actually found for the register I the number you're looking for. Then go to step 6, which is print element X found at index I, and go to step 8, exit. And if this is not the case, if the register A1 is not X, then you set I to I plus 1, so you go to register number 2, and you go back to step 2 again, and so on and so forth. Okay? So this is a simple classical algorithm for a search algorithm. And with this, you can use many different languages, so here's a collection of them. But roughly, this is sort of software independent, but pretty much that's what it will look like. And as we will see later on, the search algorithm, so typically in terms of, I already mentioned it, but in terms of complexity, the complexity of such an algorithm is that if you have a database n of n element, then the complexity is on the order of n itself. And that's where, as you will see later on, for instance, the Grover algorithm, which uses quantum mechanics rules, quantum information rule, then for Grover, for exactly the same thing, you can actually scale it to a square root of n and gain a factor a lot more, especially when n is big, than just the classical search algorithm. So this is of course an easy example, and there are different classes of algorithms. There are thousands of them, in fact perhaps even tens of thousands of them. So here I give you some of the classes of algorithm. I'm not even sure, perhaps some computer scientists probably would disagree with them or would not agree with those, but just to give you some ideas, there's the brute force, the greedy, divide and conquer, backtracking, branch and bound, etc., etc., etc. So there are thousands and thousands of them in different types and different subsets and so on. Just to give you something I found, for instance, a subdivision of artificial intelligence in a big scale. As you see already, that this the subject of artificial intelligence, so in terms of classification, then you see how it branches out to many different types of machine learning classification, where you would have supervised learning or unsupervised learning or reinforcement learning, and depending on these three, for instance, you can have other classification subsets of various algorithms that you can use. So that's just an example of a particular set of classical algorithm. So the question is, do we have the equivalent for quantum algorithm? And the answer is no, not yet. We don't have thousands and thousands of quantum algorithms. We have some of them, few of them, but what we do have, on the other hand, is examples of quantum algorithm that any of these thousands I mentioned cannot do. Okay, so again, if I talk about the two most famous, the Grover or the Shor's algorithm, none of the classical algorithms or any of these thousands I talked about can do the job as fast as these two. Okay, and those are just two examples. But the one message to take in as well is that means in terms of implementing and finding out and developing quantum software and quantum algorithm, there is still a lot to do, because at the end of the day, there are only very few quantum algorithms out there that at least can do a job that seems to be a lot more efficient than the classical ones. So for quantum algorithm, we also have families, so there are a lot less of them. I gave, as far as I can tell, there are 3 families of them. The first one is the very important one is the quantum Fourier transform family. And in this one, there is the Dutch Joza algorithm and the Simon algorithm. So we're not going to see the Dutch Joza. We're going to see only the Dutch algorithm. So it doesn't actually use the QFT, the quantum Fourier transform, so much, but the extension does. The Simon algorithm, we should be able to see that. And in this category, there is the famous Shor's algorithm that uses the quantum Fourier transform. Another family is the so-called amplitude amplification. So in one of these families, you have the Grover's algorithm that we're going to see later on. And there's also perhaps a third category, which is the so-called quantum walks family, where you have other types of subset of algorithm and problems, so something called the element distinctness problem or the triangle finding problem, and these using what's called a quantum walk or quantum random walk, which is the quantum part of the random walk. I already mentioned it, and if you remember the Galton board, I already showed you the difference between a classical Galton board where the distribution is in the center and the quantum Galton board where actually the distribution is on the side. So making use of that, you can actually solve some problems using these approaches. But we're not gonna talk about this. I just want to say a quick word before starting on our first quantum algorithm on something that is in between. So as I said, as of today, we do not have a quantum computer. We do not have a universal quantum computer. And the idea is to see, well, what can we do? So there are 2 ways of looking at it. Is what can we do to use still the power of quantum algorithm, but perhaps to hybridize it with the classical algorithm. So there is some work going on. There's a lot of interest in that to do so hybrid classical quantum algorithm, and there are 2 families of systems of problems. So the first one is so-called the quantum approximate optimization algorithm, or QAOA, and the second one, although these 2 are related with each other, is the so-called VQE for Variational Quantum Eigensolver. And I gave you an example here, just to it's just to show you an implementation of the VQE, where what they've done is that they mix classical optimization and quantum optimization. So what they've done is that they have the initial state, so they have single photons coming in, see state 0, 0. And then they had an optical chip, and we've seen that before. And in his optical chip, so you have all these sort of beam splitters and interferometers, etc. But whatever they are, what they are is they basically, through to this link here, they are basically gates. You can process quantum gates, single photons or 2 photon quantum gates. And you can reconfigure these gates through these nodes here, to these series of lines. where you can basically physically change the interferometers and basically reconfigure your small quantum processor here. And then at the end, you have detectors, output, you have a signal, and then here, you stick the response into a classical computer, and you make some optimization so that the algorithm says, well, okay, what you find is not quite what I was looking for in terms of variational method. So perhaps if you change slightly the gates or the order of the gates or the gates themselves, then perhaps we will converge more. So the CPU will give some information on to what to do next to the QPU, the quantum processor unit, to change it, to change the calculation now so that the outcomes, the outputs is changed as well, so that it gets closer to the problem we want to solve, and so on and so on. So we do a loop like this until we converge to the result we want. And for that, using this method, which is hybrid because you have a quantum part and you have a classical optimization, then define, for instance, the ground state of the molecular energy of the molecule helium hydrogen plus. So what does it look like? It looks like this. So you've got the incoming photons. So they come from this, you see SPDC, this exactly the same system. So you have the two photons, and then they stick it into this optical chip that looks like this. So this is photon 1 and this is photon 2. And they stick into this chip. So the chip here is a glass chip, so it looks like this. So you see the scale bar is about a centimeter, so the quantum processor unit is about yay big. And then you see coming out here are cables with connectors, and these are, oops, sorry. Sorry. These are the connectors. So these are the connectors, and they go onto the chip so that they can locally change the interferometer and basically change the gates that can be processed in this optical chip. Okay, and these cables are going to CPU where the optimization, the classical optimization, is done, and then a feedback to say, okay, now I've got this. So now, for instance, this is the energy you want to reach. So this is the number of optimization step. So at first, you are very far from the result, and then as you go through, so this is optimization step 1, then detectors, calculation in the CPU, we make modification, and then we send the photons again, optimization, and then by a certain of steps, so here about 40 steps, optimization steps, so loops, quantum classical, then at the end, we converge, so the variational method converge with a certain value, which is the lowest energy of the molecule we wanted to find. Okay, and they showed in this specific case that they were a lot quicker than just using the simple classical optimization from the CPU alone. So this is very much of very much interest right now, is to say, well, we have classical algorithms, so we know them very well, we know what to do with them for optimization problems. We do not have quantum computers yet, but we have quantum processors, which can perhaps help if we combine using optimization of both worlds in order to have, so that the classical optimization will help out the fact that we do not have perfect qubits and therefore not a perfect quantum computer, so that at the end we can find some hybrid classical quantum algorithm that will give us some answers and not necessarily beat a classical computer. In fact, it does not, but it would still be faster than the classical computer you would use at a given point. Right. Okay. So let's have a look at first example of an algorithm. So this is the so-called Deutsches Algorithm. So here we're going to spend some time on that. So this algorithm, so it comes from an article published in 1985 by David Deutsch. And I already mentioned that article and already mentioned that this date of 1985, because in the original article, this is where David Deutsch postulated the fact that we could build a universal quantum computer. Okay, so in fact, the title was called Quantum Theory, the Church-Turing Principle and the Universal Quantum Computer. Okay, so it was published in 1985. And in this article, on top of showing that, he took an example, which is the so-called, or sometimes called the Deutsch's problem, and he showed, which I'm about to do, that a simple quantum algorithm can process this problem faster in less steps than the classical equivalent. So what is the problem? So let's consider a binary function f. Okay, so the problem is that we have a binary function f that is a 1 qubit function. So that means that this function will go from 0, 1 to 0, 1. Okay? So that means that for this function, as we have an input qubit and output qubit, we have 4 possibilities. Okay? 4 possibilities. Because again, the input is 0, 1, but the output can only be 0, 1. So we could have the fact that both, so the 4 possibilities, the first one is that both input, okay, so both input 0, 1, will give me 0. Okay? So that means that f0 equals f of 1, and it's 0. So that's one possibility. Second possibility is that both inputs 0, 1 gives me 1. Okay? So that means that f0 equals f1 equals 1. And this means that these 2 cases is a family, specific family, which is the family that f0 equals f1. And this family, I will call it the constant family. So the constant family is that f0 equals f1 no matter what input I had. So these are the first 2 possibilities. There are 2 others, which are that inputs are unchanged after f. So what it means, that means that f0 equals 0 and f1 equals 1. Okay. So this is the third, and the fourth one is that the inputs are exchanged after f. So that means that f of 0 gives me 1, and f of 1 gives me 0. And this also is a specific family, because the specific family tells you that if f equals 0, f of 0 is 0, f1 is 1, then f0 is 1, f1 is 0. I mean, in both cases, f0 is different than f1. So this is what I call the balanced family. So it's balanced if f of 0 is different than f1. Okay? So the question I have is find out, so that's Deutsch's problem, find out whether the function is constant or balanced. in the minimum number of steps. Right? So if you were to do that classically, well, here we go, is the algorithm. You need two queries, two evaluations. So the first one is that if f0 equals 0, then you have two cases. If f1 equals 0, then you're in a constant family. If not, then you're in a balanced family. If f of 0 equals 0, then you have two choices. Either f1 is 0, then you're a constant, or f1 is 1, then you're in the balanced family. Or if f0 is 1, if f0 is 1, then if f1 is 0, then you're balanced, because it's the opposite. But if f1 is 1, then that means we are in this case where both f0 and f1 is 1, so we are in a constant case. So that means you need two queries. You need the first one, at the very least, you need this one and this one. Or this one and this one, or this one and this one. Or, if you find the other case, this one and this one, or this one and this one. But you need two of them. Okay. So let's see how it works for the quantum version. And you will see that the quantum version, for the quantum version, you only need one query. So how does this work? So this is the quantum circuit for Deutsches Algorithm. So let's go to this. So we start with two qubits, so Q0 and Q1. And we create the state, so we start with initialized state 0 and 1. Okay? And then you put each of them into a superposition state through Hadamard gates. Remember, H is Hadamard gate. So you start, so this is, so I use again try to map the quantum circuit with the mathematical notations. So if I start here, so let's write it. So Q0, so we have Hadamard gate, and then Q1, Hadamard gate. So let's say that I start Q1 in the 1 state and Q0 in the 0 state. So the initial state, psi 0, is qubit Q0, qubit Q1, which again, remember, we can write separated or in one go. So it's going to be 0, 1 or 0, 1. And then, so this where, let's put some colors perhaps. This where psi 0 would be. Now apply the Hadamard gate to each of them. So I will be in a psi 1 state. So that means I apply Hadamard gate on this one, and I apply Hadamard gate on this one. And so I'm not going to expand to it. I will assume that you understand this by now. It's going to give me 1/2 for normalization purposes. And here I'm going to transform 0 into 0 plus 1 and 1 into 0 plus 1. Okay? So if I, 0 minus 1 and 0 minus 1. So if I do this, I end up with 4 possibilities. So 0, 0, 0, 1, 1, 0, and 1, 1. So I'll end up with the 4 possibilities, which is 0, 0, minus 0, 1, plus 1, 0, and minus 1, 1. Okay. So here I'm here. So I applied Hadamard gates to each of them, and this is the state that I have. And then I put these two qubits into a box, which is going to be a 2-qubit matrix, and with the specific 2-qubit gates that I call U of F. U of F, so U has to be a matrix, so psi 2 is applying U of F on psi 1, which is the 2-qubit state that we have here. And I give a condition onto U of F is that U of F, as you can see here, has to be unitary matrix. But we do not know what it is. In fact, we don't have to know what it is. All we need to know is to make sure that it is unitary, and I will define it in a second. And so sometimes people talk about an oracle. Okay, it's something that you can see it as an oracle where you don't actually know what it is. You just know that it has to be unitary. So as long as this is, and this is the function f that we're talking about. I mean, this link to the function f that you want to probe. So unitary is a specific property. Is unitary tells you that the matrix U of F times U of F dagger, remember the transpose complex conjugate, is equal to U of F dagger U of F, and this is identity. Okay, so it's different than Hermitian matrices. Hermitian matrices is that U of F equals U of F dagger. Here in this case, is U of F dagger inverse. Okay, so for reasons that I cannot go through, so unitary matrices provides what we call unitary transformations, and they are very important in quantum mechanics because that they allow you to go from one set of bases to another. And this can only be done physically, or the physics can only be done if you use unitary matrices. Let's assume that this is a criteria that we need to fulfill for now. So what this transformation would look like if I want to unitary transformation. So an example of it is this one, is that if my my unitary matrix U of F does the following. So if I send qubit A and B, what it does, so it does nothing on A, but then on B, what it does is the XOR sum. Okay, so it takes qubit B, and you add this function that I don't know, f of A, that I want to probe. So you can show that this is unitary because if I put that again, let's do it. Yeah, if I put that again into the same matrix, I end up with A. This isn't changed, and this would be B plus, so XOR f of A plus f of A. Yeah. Oops. But the thing is that if I do plus f of A again, so according to the XOR sum, so I go one step and then I go to another step, so I go back to where I came from, then this is basically equal to B. Okay, so when I apply this twice, I started with AB and I end up with AB. Okay. So this function, so this what I chose to be, again, which is general, just the operation is particular, but the function is general. I still do not make any assumption on f, except that it's a function to go from 0,1 to 0,1, but I don't make any assumption. In fact, I want to probe this function. But what I can do is add it, for instance, with an XOR notation. And this is what this matrix does, and this is a unitary transformation, so it's fine. So that works for any f. Huh? So in particular, the one I want to look for. Right. So let's do this. So let's see what that does. So now, I've got two outputs here, and I am at psi 2. So that's what it looks like. So psi 2 equals this unitary matrix U of f applied to psi 1. So psi 1 is this. And so what I'm going to do is that, so the first qubit is untouched, but the second qubit is going to be added the function f of a. So if it's 0, I'm going to add f0, and if it's 1, I'm going to add f1. Okay, so let's do this. So I've got 1/2 of so 1/2 of 0, and then I've got 0 plus f of 0. Okay, so that's the first term. Then minus 0 of 1 plus f of 0, so minus 0 of 1 plus f of 0. Then the third term will be 1, and then 1, and then 0 plus f of 1. Again, I just apply this. So plus 1, 0 plus f of the first qubit, so 1. And then the fourth term is going to be minus 1, and then 1 plus f of 1. So minus 1 of 1 plus f of 1. Okay? No. So, as we can see here, so 0 plus f of 0, this is actually f of 0. Because 0 added to anything is going to give me the anything. Same here. So this is f of 1. For that, I don't know, because it depends on the result of f of 0. It could be 0 or 1, so I don't know what this is going to give me. Same here. Depends on what this is going to be. Here does not depend on the result. So here does not depend of f1. Whatever 0 plus whatever is going to give me whatever. So I can do that. So that's the state that we have now. So let's erase some things. Okay. So now psi 2, this is what we have there. So is 1/2 of 0 f0 minus 0 of 1 plus f of 0 plus 1 f of 1 minus 1 of 1 plus f of 1. Okay? And I can erase this, and I will also erase this. Right. So now, let's have a look at the two cases I want to test. So for psi 2, Now let's consider the two cases. So either f is constant or f is balanced. Okay, we know, and this is where we want to. So in both cases, we will see what it gives us, and we will see that at the end, by simply doing a Adama operation on qubit 0 and then a measurement, is going to give us the in one query. So one query is one measurement only. Is going to give us the whether the function is constant or balanced. But for now, so let's differentiate the two cases. So if case number one is that what happens if case number one, what happens if f is constant? Well, we know if f is constant, then we have f0 equals f1. Okay, so f0 equals f1, and this is one of the two cases we said. So if f0 equal f1, so I will not touch that. I will not touch that. This, I will set it to f0, and this, I will set it to f0 as well. So I've got psi 2 equals 1/2 of 0 f0 minus 0 of 1 plus f0 plus 1 of f0 and minus 1 of 1 plus f0. Okay? All I did is just to set f1 to f0 because this is equal. Okay? But now, what we can see is I've got f0 and f0 that I can put can factorize, and I've got 1 plus f0 and 1 plus f0 that I can also factorize. So if I do that, I get 1/2 of f0 factor 0. I must have forgot something here, like a plus, for instance. Right? So plus 1, so 0 plus 1. And then I have the other one, which is minus 1 plus f0 factorize 0 plus 1. Okay? Now I've got 0 plus 1 and 0 plus 1, so I can factorize this, and I will end up with 1/2 of 0 plus 1, and then time f0 minus 1 plus f0. Okay? And this, as you see here, so I put I can either put it like this, or I can put a tensor product the same way. That's what I did here. I don't have to do this, but it's implied that I have a tensor product, so in this case is written. What I want to say here is that 0 plus 1 is actually, I can call it's a superposition state, and that's what we call the diagonal state, so we can write it by being plus. And that's very important. Because now I'm going to look into case number 2. So case number 2, so I have no more space. So what I'm going to do is I'm going to write this and keep it, oops, and I'll say this is case 1. So case number 2 is the case where f is balanced. So I can erase this. Okay. So f is balanced. So if f balanced, So in this case, we said that F0 has to be different than F1. But what does that mean? Now, if F0 is different than F1, that means that when I'm going to have F0 here, then this operation, 1 plus F0, has to give me F1. So this has to be F1. Likewise, here I've got 1 plus F1, so I start with F1. So this has to be F0. Cannot be F1, because I start from F1, and this function has to give me the balance term of F1, which is F0. Well, I'll put it in red. Okay. Here I forgot that, by the way. That's for case 2. That's for case 2. All right, so now let's rewrite this for the case 2, which is that psi 2 now is 1/2 of 0 F0 minus 0 f of 1 plus 1 f of 1 and then minus 1 f of 0. So I have F0 here, F0 there, so I can factorize it. And I have F1 here and F1 there. I can also factorize it. Except that now I've got 0 minus 1 and minus 0 plus 1. So let's write it. So I've got 1/2 of say 0 minus 1. So tensor product this time. Again, I don't have to put it. It's implied, but let's write it. It's in my slides here. And then F0 minus F1. Oh. Yes, correct. And now this state is the diagonal state. Which I can, the anti-diagonal state. I remember this is if plus is like this, so if 0 is like this and 1 is like this, then 0 plus 1 is like this, and 0 minus 1 is like this in terms of vector in 2D vectors. Okay, so this is for case 1. That's what we found, and this is for case 2. So if I summarize, so I can rewrite psi 2 so summarize. To summarize, if constant, which is case 1, psi 2 equals 1/2 of plus, and then F0 minus 1 plus F0. And if balanced, this is case number 2, it's this one. I've got psi 2 that would be equal to 1/2 minus F0 minus F1. Okay? Voilà. So this is for the top qubit, so qubit Q0. This is why the tensor product is important. Because in fact, if you remember, we did the same thing for the quantum teleportation protocol, where what we did is we rewrote in a different way the states. And by doing so here we reorganize it as well, so that at the end what it looks like is that qubit 1, if qubit, so in the case of constant, qubit 1 will be plus, and qubit 2 will be something like this, which we will see, I don't care. I don't want to know what it is. I don't need to know. Or, if it's balanced, then the top qubit number 1, or 0, is going to be minus, and the bottom one is going to be this, which is also something I don't know, but I don't care. I don't care because now what I can see is that if I am constant, then the top qubit is going to be in a plus state. And if I am balanced, then the top qubit, then the top qubit is going to be minus. But that I can tell. I can tell very easily, because if I do Hadamard gate on this one, and nothing on this one, so I just let it go, I don't measure it, I don't need to know, because all the information will be given here. So if I make a measurement, so this, like this. So I've got the answer. So if I do, and what it means is that if I do a Hadamard gate, that means I retransform plus and minus into a 0 or 1. So it means, that would be what is called here psi 3. So psi 3 only applies on this qubit, where I do Hadamard gate, and Hadamard gate will transform a plus into a 0 and a minus into a 1. And all I need to know there is to know whether I have a 0 or a 1. That's all I need. Because if I have a 0, that means I was before the Hadamard gate, I was in a plus state. That means, therefore, through this transformation, I had a constant function. But if I measure this, if I measure 1, okay, so if it's 0 or 1, if it's 0, it's constant case. But if it's the 1 I measure here, that means I was in a minus state before the Hadamard gate, and therefore, if I was in a minus, that means I was in a balance case for the function. So, in other words, in one query only, just one measurement, whether I have 0 or 1 at the output, I can tell whether the function was constant or balanced. So here, if I have 0, it's constant, and if it's 1, it's balanced. Okay, because the 0 is basically mapped onto this case, which is the constant case, and the 1 is mapped onto this case here, which is the balanced case. So in one query only, I have the result. Okay. So this is the simplest algorithm you can think of. Already shows that you can. So no matter what you do, in order to find whether the function is balanced or constant, you need two queries in a classical case. As in here, by only one measurement, you get the same result. And that was, so in 1985, that was the first actual implementation of an algorithm where it was shown that quantumness that we use here is more favorable and faster and requires less measurements than the classical one. So, as I said earlier, well, this is nice kind of proof of principle. For application, the applications are next to zero. That's not very useful. But then afterwards, the the version called the Deutsches Algorithm, and then there is also another one later on with some other colleagues of them, is more interesting because what you do is you basically get the sign of a function amongst the say a register of n qubits. So they extended that kind of query and that kind of problem to n qubits and find the sign of a given function. You don't know the function, but what you can tell is what's the sign of the function applied to n qubits. That already has some application, and that led to other algorithms like the Simon, and in particular the Grover and the Shaw algorithm, which are kind of related to this problem, which are definitely applied to problems. We can be definitely applied to problems. Voilà. So one. So that I said that right. I just want to say to finish on this part. So before going to the next algorithm, which is going to be Simon and Grover. So not next week, but the week after. I just want to mention that the so-called many-world theory. So don't know if you heard of that. So you may have heard of it from Marvel movies. Then you can have a multiverse. So you can be in different universes at the same time. But actually, so from this movie, they actually took that idea from a very serious idea that was called or serious at least by the author who wrote it, that's called the many-world theory of quantum mechanics, and that's the theory built by Hugh Everett. And in this, so this was in this article, so it's called Relative State Formulation of Quantum Mechanics, so that dates back 1957. And if I want to explain, so basically what the many-world theory tells you, if I want to explain superposition, I could explain it by the fact that if I have many universes next to each other, then a superposition actually means that you are in a 0 or 1 state, but you are 0 in one universe and 1 in another universe. So if I take the Schrödinger's cat problem, so the Schrödinger's cat, remember, is either dead or alive. Well, in this theory, it tells you that actually, yes, the cat is dead and alive at the same time, but not in the same universe. That the cat might be dead in one universe is number 1, and the cat at the same time is alive, but in another universe that branched out somewhere, somehow, in universe number 2. So in other words, what the many-world theory of quantum mechanics tells you, that right now we are in a universe, this is our universe where I'm standing in front of you, but there is another universe number 2 or 3 or whatever, where I'm already done with my course and I'm somewhere else in my office. And then there's another universe, or actually we made a mistake and no one showed up to my course and there's no one in front of me, and so on and so forth. There's another universe, or my tire was burst and I couldn't come to the lecture, and so on and so on. So all of those many-world theory possibilities exist at the same time, and that the reason why we are in the universe that we are right now at each step is due to this decoherence mechanism I was telling you, is the fact that you're looking at me right now makes sure that I cannot be in a superposition state, or I cannot be in another state in my office at the same time. Because you, in a way, are making sure that we are connected in the same universe. But in another universe, I could be doing something else, or you could be going to the canteen already. Okay, so in this particular case, that means that both possibilities of the function being constant and balanced do exist at the same time, but one of them, so the function being constant, is in a parallel universe of the one that is balanced in our universe. Okay, when I made the measurements, I find this or this, but that means that the counterpart is in another universe. Well, this is a nice theory, at least. Well, it could be. We can like the idea of it. It's not liked by everyone for many good reasons, and one perhaps the best reason for not liking it is the fact that this is almost by construction is impossible to test experimentally. And this, for physicists, is something that is very difficult to understand, where we give you a theory, nicest theory you can think of, but we tell you at the same time, oh, but hang on, you cannot test it. So this is already a big problem. There are also other major issues on this theory, but at the end of the day, it's a theory. It's a nice theory, and the reason why I talk about it is because I believe that David Deutsch is a big believer in that theory. Right. So anyway, so with this, I will stop here for today. So just a quick reminder on what we said. So this is what I call quantum algorithm part 1. So it's a slow introduction to quantum algorithm. So next lesson, so it won't be next week. So the next week there is no lesson. So the week after that, there will be quantum algorithm 2. So most likely it will be at a different time, probably at 2 p.m. French time. And it will not be given by myself. And we will talk about the Simon algorithm and the Grover's algorithm. And next, as we saw, we will start to see people from companies to talk about quantum sensors and quantum cryptography. So with this, I will stop for today. Thank you for your attention and see you in a few weeks' time.